Hi everyone, welcome back to the channel, and in today's video we are going to discuss how column generation helps with better relaxation. So that topic. I have also written the date for today's video here. That's because today is my birthday, and what better way to spend my birthday than doing this kind of recording, right? So also I'm experimenting with showing my face on the video. So let's see if that helps. And okay, that's enough for blabbering, and let's get started with the topic. Okay, so we will start with bin packing. That's a very standard problem in column generation that we use for learning things. So we'll start with this, and then we will see that it has bad relaxation, and then we'll dive into different topics like Dantzig Wolfe decomposition and Minkowski-Weyl theorem and all the things that eventually helps us guide why the column generation model with bin packing helps with the linear relaxation, right? So let's start with the problem first, right? So we have n bins. All of them have the same capacity, let's say B, and we have m items, right? All of them have different weights. Let's say each item I has the weight di. Okay, so the goal is that we want to fit all these m items into this n bins, and we want to use as few bins as possible, right? So all items cannot fit in one bin, so that's a trivial condition. That's otherwise the problem is like very simple, right? So put all the items in one bin and then we are done. So sum of all di is strictly greater than b, let's say. So we need at least 2 bins or more than 2 bins in general, and we want to minimize the number of bins that are needed to pack all these items, m items. Okay, so a standard model for this kind of problem is something like this. It is xij, right? That's a binary variable that denotes that item I should go to bin number j. Okay, and then we have another set of binary variables, let's say yj, that basically says if bin j is used. Okay, so now let's see, using these two variables, how we can write the complete model, right? So the objective is that we want to use as few bins as possible, so we are going to minimize sum of bins, right? So bins used, it's yj is the one that basically says bin j is used, so sum of yj, and that sum should be overall j, right? So that's pretty simple. The one of the constraint would be that each item has to be packed in some bin, right? So I have xij, right, and I have to sum over all bins j. That item I should be packed exactly once, right, or at least once. If it is packed more than once, then we can deal with that. We can remove that redundancies later, and that is true for all I. Okay. There is a constraint that has to link these two variables, right? So xij and yj. So that part is trivial, right? So I will say that xij is less than equal to yj for all ij, right? So if I'm putting any item in bin j, then that bin is marked as it is being used, and so yj should be set to 1. And the last one is pretty simple. It's a simple capacity constraint. So we are going to say that if I'm using item I in bin j, then its weight di should be counted, and that sum of all of those weights, right? So sum of all of those weights should be less than equal to the capacity b, and that should hold for all bins j. Okay, so this is the standard model. Now you can make it slightly better by having this constraint a little bit tighter. By you can just say that, you know, this bound is tight only if bin j is used. Okay, so this part will make it slightly tighter than what it is right now, but other than that, I think this part is still not needed. I mean, you can without this part also the model is still correct. Okay. Now, so there are two problems with this. So one is symmetry, right? And so symmetry is basically I can have let's say item 1 and 2 in bin number 1 and item 3 and 4 in bin number 2, and I can swap this two, right? So I can put 1 and 2 in bin number 2 and 3 and 4 in bin number 1, and that's exactly the same solution for our purposes. So that's kind of an extra work for solver to remove all of these equivalent solutions. So either with pruning or with finding solutions, it has to basically iterate through all of these solutions, right? So that's kind of a lot of hard work for the solver. So if for some reason I have eliminated this 1, 2 in 1 and 3, 4 in 2, that solution is, let's say, not good, then I also have to do extra hard work to eliminate 1, 2 in 2 and 3, 4 in 1. So that's kind of annoying. But the bigger problem is relaxation, right? So symmetry is also a very big problem, but there is another big problem which is called bad relaxation. So, okay, so let's try to understand how bad this relaxation is, right? So, okay. So if you think about what is the minimum number of bins that are needed, right? So what is the lower bound for this problem, for a relaxation problem, right? So if you can basically identify something, if you just assume that these items are all liquid items, right? So you can basically break one item into two parts and put half of that item or 1/3 of an item in a bin. If it doesn't fit completely, then all of those things you can do. In that case, it should not be very hard to realize that the lower bound, let's call it L, should be basically sum of all di divided by b, right? So I can basically have all my items. This is the total weight of all the items, and I can just divide it by the capacity of the bins, and that many bins I will obviously need to use, right? So that's basically seal of this, but let's say even this is a lower bound, right? Now I claim that there is a solution for in this this problem, right? So if we just relax this problem to continuous variables, then we can find a solution that basically achieves this bound, which is kind of a bad news, right? So that solution is something like this, right? So I can set all yj variables to this L by n, right? So this objective, if we sum over all yj, that will be exactly L because there are n bins, right? And I can set xij equals 1 by n, right? So over here, all the constraints will be satisfied. The first one is sum over all I, sum over all j. So we have n bins, so sum over n bins, 1 by n is going to be equal to 1. So this constraint is satisfied. Xij is clearly less than yj, so because L is obviously greater than 1, because otherwise the problem is trivial, right? So and the last constraint is also kind of satisfied. If you want to verify it, you can verify it. So this is sum of di by n, and that should be less than equal to b. Things you can basically say that this thing is less than or equal to n, right? So the total number of bins that we have, right? So this is the lower bound, and that means number of bins that we'll be using. So if you just swap b and n, then you will quickly realize that this inequality is also satisfied by this solution, right? So the point is that with this solution, we are already reaching the lower bound, and that basically means that it is a bad relaxation. The actual answer for the integer problem is a lot bigger than this trivial lower bound, right? So okay, so for the column generation model, what we are going to do is we are going to use different types of variables, right? So now consider this kind of a pattern, right? So let's say this is one bin, and I am putting item number 4. So let's say its weight was d4. Item number 5, let's say it's d5, and so on and so forth. So let's say I will also put item number 3, and let's say this portion of the bin is empty, right? So this is one good pattern. I can use it in my solution or not use it in my solution. So if I have a variable for each pattern, right, then I can basically avoid this symmetry problem, right? So I only have to consider a pattern once, and I don't have to, if I eliminate a pattern, I decide that this pattern is not good, then I don't have to eliminate different parts of the subtree for the same pattern, right? So that's the way of avoiding symmetry. Okay, so we can basically look at different patterns as well, right? So this is one pattern. That there can be another pattern, something like, let's say D2, which is a lot bigger, let's say, and D1, which is like this, and then this part is empty, right? So this is also another valid pattern, and I will have a different variable, let's say lambda2 for that, and so on and so forth. So these are my variables now, and I have to decide whether individual pattern should be used in the solution or not. So that's my problem now. So my objective will be minimize sum over lambda j, right? Overall j, let's say, right? So some over lambda j is my pattern, right? So how many different types of patterns am I using? That many bins I'm basically using, and that's what I'm trying to minimize. And my constraints are pretty simple, like, so each item has to be packed at least once, exactly once, or rather, right? So let's say I have this pattern lambda j, and I want to know that for item I whether it is packed in it or not. So let's say I have this coefficient which are well known, right? So let's say a ij, that basically denotes whether this item I is present in this pattern or not. If we have this this variable as lambda1, then for I have 4, 5 and 3, so a4 1 will be 1, a5 1 will be 1, 3 1 will be 1, but a2 1 will be equal to 0, right? So this basically denotes whether this item is present in my pattern or not, and I have to cover it, right? So this, let's say I will sum over all possible pattern, and that should be equal to 1, right? And this should be true for all I. Now I can basically make sure that I don't have to consider all possible pattern. I have restrict my attention to only maximal patterns, right? So if I have to also consider, let's say, this pattern, which is just d4 and d5, right? d5. I can actually fit d3 inside it, but let's say I'm choosing not to fit it, right? So I'm saying that I don't want to consider this type of pattern. So this is not a maximal pattern. The problem is that if I can basically add d3 to it, and this pattern is strictly better than this pattern, right? So this is obviously a subset of this pattern. So I don't want to consider this type of pattern. I only want to consider maximal patterns in which no more items can be added, right? So if I restrict my attention to this, then I can basically relax this constraint a little bit. I can say that this item has to be covered in at least one bin, right? So instead of equality, I can use a greater equals. So if it is used in more than one bins, then I can basically remove that item from some of the other bins, right? In my final solution, in the post-processing step or something. Okay, so that is my problem now, and that is something that I have to solve. Now the problem, obviously, with this problem, with this kind of a formulation, is that this has just too many columns, right? So if you try to think of how many patterns I'm considering, right? So for each item I have two choices. Either I put that item in that pattern or not. And so there are 2 raised to m possible choices for m possible different patterns, right? So this many different patterns are there. So basically for each of them I have one different lambda variable. So that many lambda variables are there. So that's just too many, right? So what we do is that we use column generation to solve this problem. So we don't use all the lambda variables at the beginning, right? So initially we will use let's say simple patterns. Let's say one item, that basically some feasible solution of this problem, some feasible solution that is very easy to find. We start with putting one item inside each pattern, and those are the only patterns we can consider at the beginning. Okay, so that's obviously not going to give me the optimal answer. It basically makes this problem feasible, but it's not optimal. So we will have to generate the like a good kind of patterns through a different way, right? So we will call this a restricted master problem, right? So this entire problem was master problem, but if we are only considering a subset of patterns at a time, then it is called the restricted master problem. Okay. So how do we generate patterns that are needed, right? So let's say we are going to solve this thing using a simplex method, right? So this is a linear program, LP, linear program, and we are going to use simplex method to solve this. Then how do we solve things in simplex. It's like basically we have this simplex w in which on left hand side we have this basic variables, right? These are the ones that basically take non-zero values, and these are all the other non-basic variables that typically are taking the value 0, or they are basically at one of the lower bounds or upper bounds, one of the bounds basically, right? And the way we change things, right? So way we enter one of this variable inside the basis is basically like we look at this variable's reduced cost over here, and if that is negative, then we can basically enter this non-basic variable and then kick out one of these basic variables and then put it over there, right? So that's precisely the same process that we are going to follow, right? So let's assume that the dual variables for this constraints are pi I. Okay, so if we solve a simplex tableau, right? So for if you solve this problem to the optimality, then not only we'll have the values for lambda j's, we'll also have the values for pi I, right? So simplex method we can basically calculate the dual solution as well. So we know the dual values, which is pi I, and now I want to calculate the reduced cost of some random variable lambda j, right? So what is the reduced cost of this entity? What is that entity for some random variable lambda j? So all of these variables which are taking non-zero values, they are basically the basic variables, and for them the reduced cost is going to be 0. But let's say some hypothetical variable that I haven't added yet in my restricted master problem, I want to calculate its reduced cost. How can I calculate it? So the formula for reduced cost is basically you should look at the constraint in the dual for that, right? So for every variable in the dual I have a constraint, and in that constraint I will have a slack variable, and the value for that slack variable will be equal to the reduced cost in the primal for that variable, right? So if I look at this constraint, right, so this constraint will be something like for this dual constraint for this lambda j variable, it will be like aij, yeah, that thing is basically pi I. These are my dual variables, these are coefficient. That thing should be basically less than equal to 1, right? So that thing is less than equal to 1. So if I have a slack variable, right, so I can basically convert this into equality, and if I put everything, all of this thing on the other side, then my reduced cost expression will become 1 minus sigma aij pi I, right? So that's the formula for my reduced cost. Now the problem is that I don't know whether what are the values for this aij, because I haven't yet added this column in my restricted master problem, so I don't know if that column exists. What is that column? I don't know yet, right? So I don't know the values for aijs as well, right? Because I don't know what the pattern is, therefore I don't know whether each individual items are present in that pattern or not, right? So that's a problem, right? So this is basically an issue, right? So we are also not looking at a particular j, right? So we are basically trying to generate a random problem. So I'm going to reduce this notation to, let's say I will call this zi, right? So and this is basically the sum over all I, right? So this is sum over all I. So this is the formula for my reduced cost, and what I'll do is that I'll say that I don't know these things. So these are my variables, and this is the expression of reduced cost for that for whatever pattern that I'm trying to generate. So I'm going to minimize this reduced cost, right? Minimize this thing, and zi are my variables. So I'm basically generating a pattern that minimizes this reduced cost. And if the reduced cost is negative, then I can based on the values of this zi, I know what is the pattern, and then I can add it to this, right? So that's the idea behind it. The only thing that we have to make sure is that we are assuming here, right? So we are assuming valid patterns. And by valid patterns, I mean that these patterns, they only contain items that don't exceed the capacity of the bin, right? So that is something that we have to make sure in while I'm trying to generate this pattern. So I can add that as a constraint. I can basically say that sum over di zi. So if I decide to put I in my pattern or not, so that is zi. So if I'm putting it, then I'm calculating its weight, and that should be less than equal to b. Okay, so this is my constraint and this is my objective, and this is a nice integer program. We'll call it a sub problem. Right. So the process for solving this entire problem, it goes like this. I will start with some random patterns, right? So let's say one pattern in which every item is present, one pattern for each item, let's say, and then once I solve it, I'll have this dual cost, right? So this pi variables, one iteration of simplex, or the optimal answer for that simplex, right? So this is still we are still focusing on LP, right? So we are not focusing on the integer version of this master problem. So once we have that pi I variables, I can use this pi I variables and put it inside this sub problem, and this sub problem will give me two things, right? So either it will give me a pattern that has negative reduced cost, and then I can basically put that pattern back inside my restricted master problem and then solve this problem again. Or it will say that the smallest possible reduced cost is greater or equal to 0. In that case, I have already proved the optimality for this LP, right? So that's how we are going to solve this linear program in here, right? So overall, obviously, these Lagranges are binary variable. So this is just the solving the linear program part of it. So this is like solving the root node linear relaxation. And then we will have to branch on it, and then in each branch we have to do the exact same process, right? So we will have to generate more columns and then solve the linear relaxation and so on and so forth, right? So this entire process is called branch and price. So this, if we are solving just one LP, the root node LP, this is called column generation process, right? So the only benefit is that there is avoid symmetry, and the second benefit is that my claim initially that I made, that this basically is a tighter relaxation. So now we are going to look into why that gives us a better relaxation. So we'll start with Dantzig Wolfe decomposition. Right. So what is this? So let's say I have my linear program in my standard format. Let's say I have this C transpose X such that AX is greater or equal to B. That's my standard problem. And let's say I'm actually going to divide my constraints into two parts, right? So one set of constraints are AX, so this is minimization, by the way. One set of constraints is AX greater or equal to B, and the other set of constraints, let's say, are DX greater or equal to D. Okay. So let's say I have divided my constraints into two parts in such a way that these are my easy constraints and these are, let's say, my hard constraints. So this can happen, right? So there are in your linear program, there are certain constraints for which it is kind of very easy to solve the linear program and very easy to even solve an integer program. But there are some this annoying constraint, which are, let's say, sometimes linking constraint or other type of constraints, which kind of make things a lot more harder. Right, so we are going to split those two constraints, and we are going to use a theorem by these two people, right? So Minkowski and Weil. So these two people said that my linear program, right? So when I have a linear program, it basically is some sort of a polyhedron, right? Like something like this. Right, and these two people say that I can represent my linear program like this, like so. For let's say I'm going to consider this part of the linear program, right? So this is some polyhedron. Sometimes it's unbounded, but let's for now focus on the bounded parts, right? So this is my linear program, and these two people say that I can represent this thing like this also, and there is another nice representation which it takes into account the extreme points of this polyhedron, right? So these are my extreme points of this polyhedron, right? There's 5 points, let's say, and I can represent any point inside this polyhedron as a convex combination of these 5 points, right? So that's the theorem by these two people. So if my polyhedron is unbounded, then I will also have extreme rays, and then that also comes into the picture, like how I can represent a point inside that. But let's for now assume that my polyhedron is bounded, right? This part is somewhat easier. So I can say that these are my extreme points. So I can say that any point inside this polyhedron X, right? So I can represent it as my extreme points, which are fixed, right? So these are my 5 extreme points. It's some combination of that. Wait, okay. I'm going to use this. Okay. So some combination of that, right? So let's call that combination lambda p, right? And the only constraint that's that other extra constraint that we have to add is that sum of lambda p should be equal to 1, right? So we don't want to represent this point over here using these 5 points. So it has to be inside this polyhedron, right? So that's a represented. That's a way to represent this point inside it. Okay. If I have extreme race, basically my polyhedron is unbounded, then I can also add this extreme race, right? So I will have a direction like this. Let's say in this direction it is unbounded. So this is, let's say, a vector 4, 1. Then this 4, 1 becomes my extreme ray. Same as extreme points, just some coordinates. And then I multiply that by lambda r. I can sum it over all r. And this sum, the sum of lambda r doesn't even need to be equal to 1. So this is kind of free. And this is not free, right? So this, okay, I mean not free. This one is also like kind of, I think it's greater or equal to 0. All of this is greater or equal to 0, lambda p and lambda r. But yeah, so sum of lambda p has to be equal to 1. So sum of extreme points, the combination that I'm using, that has to be equal to 1. If I pick a different point, this point, then this lambda piece will change. The x piece remain constant. Right? So I can basically represent all this point inside this polyhedron by doing things like that. So I'm going to do something crazy on this, right? So I am going to do weird stuff by basically, I'll say that, you know what, I am going to substitute this constraints inside this constraint, but not in a standard way, right? So how I'm going to do this is that I will take this easy constraint. I will take this polyhedron representation for this easy constraint, because it's easy constraint, so I can very easily find out what are the extreme points for that and everything. So I will find out these extreme points of that, and I will list out all of those extreme points like this, right? And I will represent x like this, right? And I will substitute this representation of x inside this constraints, right? So my constraints now will become a times x instead of x. I will write all these things, right? So sum of lambda p, xp, and other stuff, this other stuff, right? All of this is now greater or equal to b. And of course, obviously, sum of lambda p is equal to 1. That I have to explicitly add it here. So now, since I'm only looking at this way of representing things, and this way I can only cover the points which are inside this polyhedron. So I'm never looking anything that is outside dx greater or equal to d polyhedron. So if I'm looking at this formulation, I know that I am already satisfying these constraints, and I have substituted that representation inside this constraint. So now I'm also satisfying this constraint. So I don't need to write this constraints explicitly, right? So this is my entire problem with this objective, right? So this is another way of writing that same problem. Now, as I said, like you can probably see the traces of column generation happening right here, right? So the number of extreme points for a polyhedron can be exponential, and so therefore over here also, right? So this lambda p's are my variable, x p's are fixed. So this lambda p's are generated on demand, right? So we start with fewer lambda p's, some extreme points basically, and then this we basically add them to this problem, which is now my restricted master problem, right? So I will add this lambda p's by solving by basically finding dual cost of this constraints, and then putting it inside going to this polyhedron, and then we'll have some objective for the reduced cost expression, and then we basically minimize that reduced cost expression, and then it will be one of this extreme point of this polyhedron, which is kind of, as I said, it's easy to solve, right? So that's my entire focus. And since it's easy to solve, we can very quickly find an extreme point that basically gives us negative reduced cost, and then that extreme point we will add it inside this formulation, right? So that's how we solve this problem. So what is the point of doing all those things? So let's talk about that now. Right, so we have split the constraint set. So let's say this is my first set of constraints. I'm going to draw some polyhedron for that. Right, let's say this is dx greater or equal to d, and let's use a different color for the other one. Okay, so we will use this color and do crazy stuff like this. And let's say this is another set of constraint ax greater or equal to b. Right, so the all of this intersection region, the blue curve, blue polyhedron and the green polyhedron, this part is my feasible region. Right, so this I mean, this is, if I do all that substitution and that dx greater or equal to d, I just represent that by my this extreme points and then put it inside this ax greater or equal to b, then I'm not really doing much of a difference in terms of relaxation here, right? So all of this is basically LP. Now the benefit comes when I am going to solve this dx greater or equal to d, this constraint, right? So which are the easy constraint. If I'm going to stress on this part a lot more. So these are easy constraint. I'm actually generating, I'm actually solving this using an integer linear program, right? So I'm actually finding this extreme point using an integer linear program. So now let's see what happens, right? So if I look at the feasible region of this integer linear program, so this will be like dots like this, right? These are my feasible points. Let's say this one as well, like this. Do we put this? Okay, let's put this one as well. Right, so this is my feasible region for okay, here also one more. This is my feasible region for dx greater or equal to d, and not feasible region, but feasible points. Right, so if I'm solving it using an integer linear program, so I'm generating the extreme points of the convex hull of this, right? So let's draw the convex hull for this, right? So it will be something like this. Yeah, I'm kind of struggling to draw straight lines, but it's okay. Either ways, right? So my extreme points are this one, this one, this one, this one, this one, and maybe this one, right? So these are my extreme points. So when I'm generating my extreme points to substitute using column generation and to put it inside this constraints, right? So I'm using these points, I'm generating these points. So effectively, right, my feasible region for the column generation restricted master problem LP is not this entire blue and green region intersection of this, but instead just this part, right? Because I am only generating this extreme points, not this ones, right? So this is now clearly a tighter relaxation than my original intersection, right? So that's how it actually helps with the linear relaxation. So now let's try and go back and see the same thing that we did with the bin packing problem. Okay, so let's go back to our bin packing example, right? So we have, this is our standard model and this is our column generation related model, right? So we have restricted master problem and sub problem and all the stuff. So let's try to see how we did those things over here, right? So these are my easy constraint, right? So this one's, right? So I am putting that inside my SP sub problem, which is right over here. Recall that they look basically exactly the same, right? So di xij is less than or equal to b. This is di zi is less than or equal to b. This is all sum over all I, right? So it's exactly the same constraint, and this too, right? These are my harder constraints. So I'm basically substituted that thing right over here. This is my part of restricted master problem. So I'm using a different representation right over here, right? So I'm using this lambda j. That's because I am now I basically reformulated this master problem, this set of constraints into by substituting this the extreme points of this set of constraints inside it, right? So it looks now the lambda format, right? So these are my actual extreme points for this subproblem, right? So this is now substituted inside this, and because this relaxation was bad, and since now I am solving this subproblem using integer programming solver, now I'm generating the extreme points of the convex hull, and therefore this basically gives me the tighter relaxation, right? So I think that's the end of this video. This is also something that I actually covered recently in my column generation introduction to column generation workshop. So there are other things also I covered in that. So hope you liked it, and don't forget to press the like button, subscribe button if you haven't subscribed already. I'll be trying to add more and more videos in the future, depends on how much time I'm getting, but yeah, that's all from now. Thank you very much. See you next time.